In developing radiative processes of atoms, it's important to know about what the possible configurations for electrons are. And as we've talked about, that's all about trying to minimize the energy and to try to place electrons in the appropriate orbitals subject to the Pauli exclusion principle. So what we're going to work on now is talking about spectroscopic terms. And spectroscopic terms are all the possible allowable configurations for a given atom and with its electrons. So we have to think about, when we're doing this, a couple of different points. So one of those points is that we need to think about what are equivalent electrons and what are non-equivalent electrons. So all of this is about spectroscopic terms. And to derive a spectroscopic term, you describe the NL orbital, and then you consider all possible M and MS, so the orbital angular momentum, all of the M and MS states that could be for that given NL configuration. So we consider for NL orbital, all possible M and MS for electrons outside the closed shells. And from that, we figure out S and L, and we can then work through the energy levels. Now, we can consider two different things, equivalent and non-equivalent electrons. So equivalent are those that occupy the same NL orbital. So for example, 2p. So electrons occupying that one could be equivalent electrons. Non-equivalent electrons do not occupy the same NL. So an example there might be something like 1s, 2s, an electron in the n equals 1, L equals 0 state, and the n equals 2, L equals 0 state. Now let's think about how we write out spectroscopic terms for these different configurations. So let's deal first with the non-equivalent electrons. So for non-equivalent electrons, let's take an example. Let's take the example that I gave before, 1s, 2s. So both are in the s orbital. So L is equal to 0 for both of those, which means that the total L, which is equal to L1 plus L2, is equal to 0. And the spin could be either up, down, which is just as equivalent to down, up. In that case, S is equal to 0 because we have 1/2 plus minus 1/2. And in that case, we would have a 1s descriptor. I'll write that down in just a minute. Or the spins could be up, up, which is equivalent to down, down. And so the total s would be equal to 1. And this would be what's called a 3s. Now, the first one of those is what's described as a singlet. And the second one of those is what's described as a triplet. So this is a singlet. And this is a triplet. So the spectroscopic term is written as 2s plus 1 L J, where J is the total angular momentum. So we're going to ignore J for a minute right now. And L is the orbital angular momentum number written as S, P, D, and F. So in this case, where I've described something where L, the total orbital angular momentum, is equal to 0, then that's a sharp configuration. So we write that as S. So that's where I replace my L with an S. And I have 2s plus 1 as the term that comes up here. And the 2s plus 1, I've said that s could be either 0 for my singlet state, or it could be 1 for my triplet state. And so this term can be 1, which is 2 times 0 plus 1 equals 1 s, and that's my singlet. Or alternatively, I can have 3s, that's 2 times 1 plus 1 is equal to 3. That's my my triplet state. So you can see where the names singlet and triplet come from, based off of the term to the left. So you need to recall on this that L is the orbital angular momentum number, and we'll always write that as SP for L equals 0 or L equals 1. Now, in order to get the case, if you imagine a situation where we have electrons in a single NL, so now if we consider the case of equivalent electrons, and equivalent electrons come from having, for example, something that's the example of 1s2, where it's a little s2. We have 2 electrons both in the s orbital, and they're both in the n equals 1. So for that to happen, because of the Pauli exclusion principle, they have to have their spins opposite. So in this case, for the 2 electrons, we have L is equal to 0 for both of them. So total L, which is equal to L1 plus L2, is just 0. The spin has to be aligned, or they would otherwise be the exact same indistinguishable electron, and that wouldn't be allowed. And so S has got to be equal to 0. And so in this case, the only state that's allowable is a 1s state. And actually, it's worth remembering that the terms are actually written as 2 s plus 1 Lj, where J is given by the orbital angular momentum, it's the total angular momentum, plus the spin angular momentum. And so in the case that I've just written above with my 1s2 electrons, this would become 1s0, because little s is 0 and L is 0, and the total angular momentum is 0. And we'll need to return to that when we come a little bit further along. But for the time being, we'll just pause there, and we'll pick up as we carry on in our next set of lectures.